Hello, everyone. I remember as a small child looking at my dad's stereo, and to sort of date myself, this stereo not only had a cassette tape section, it also had a record player on top of it. In fact, I recall it was either me or my brother breaking the turntable once while we were practicing our latent DJ skills. And I'm just going to say it was my brother because he's younger, so he deserves the blame. Incidentally, that's called logic. You should look it up. It's definitely legit. Anyway, the relevant feature that I'm referring to and why I brought it up is the cassette player section because back in the old days where the term digital output basically meant you had a finger painting, there was an analog counter that measured how much tape had passed. And this was basically just, three plastic discs with numbers on them. And they were all set back inside the stereo with a tiny horizontal slot that let you see just one number at a time on each dial. So there was also a button that you could press that would set all of it to 000. And then when you hit play on the tape, the discs would each start to rotate and it would start saying, 001 and then 002 and so on. So this way, if you wanted to return to a spot in the tape, you just wrote down what the number was at that time. And then later you could fast forward or rewind the tape until those discs were at that same number and you pick up right on the same spot where you were looking for, right? I was probably about, 3 or 4 years old. And I remember watching these wheels turning. And honestly, it kind of fascinated me even before I understood what the digits were actually representing. And of course, once I could count, it was even more interesting at that point. I just loved how the front of the counter would stay at 00, and then that last wheel would be turning, and suddenly it would get to 009, and the very next time it would rotate two discs, and suddenly you would have 010. And so this blew my little brain, and I was thinking, I guess it said something about my nerd nature that I can remember watching those numbers more than I remember exactly what we were listening to on those cassette tapes at the time. But why am I reflecting on all of this now, today, in 2022? Well, as I mentioned a bit in passing in the previous video, I think this is an accurate representation of what numbers themselves really are, by which I mean specifically all numbers are just loops. And not only that, but mathematical operations that we do are really nothing more than loop manipulation disguised as some kind of esoteric process we label mathematics. See, in my opinion, the vast majority of the nature of mathematics is obscured by the teaching on the subject. It's sort of like we're teaching the form so you can ignore what we're actually building by teaching the form. Basically, you're only interested in getting the right process to get the correct results. And we never really take a step back and just take in what we are actually doing when we do mathematics. See, mathematics is primarily taught these days in a utilitarian way because it is so useful in so many different arenas. I mean, you need math to balance your budget, to design a weight-bearing support beam in a building, to launch a rocket into space, to make sure the GPS on your cell phone gives you an accurate direction to the nearest Burger King. And so we study formulas like we're cooks baking recipe, but we never actually sit down and think about what are these ingredients that we're using while we're following these formulas. When I was in high school, the only mathematics course that I genuinely loved right from the start, day one, was geometry. And that's because geometry is visual. Not only is it visual, it's also tactile. Now, both of those learning styles fit my personality. Not only do I watch and observe, but I like to experiment and test things out. And I'm perfectly fine just throwing out something random and to see from that what happens to the system that I just threw this random chunk into. To give kind of an example of what I mean by this is I remember my geography teacher once looking over one of my proofs, and I'm not going to give the exact statements of what was said because I don't want to dox my childhood, but basically my teacher said something along the lines of, This proof is like you're driving from Tampa to Orlando with a pit stop in Seattle. And, despite all that, I mean, you do get there in the end. That was essentially the gist of it. You're going the long way, extremely long way, but you do get there in the end. And you might be asking, well, what exactly did I do that made it so complicated to get there? Basically, for the problem, we were just told things right from the beginning saying, use these as your given statements. It hadn't yet been taught. It was just saying, use these, and from these statements, you can prove this outcome, so go ahead. And what I did is I actually went before that to the axioms we had actually started with and used them to establish the proof of those formulas that we could then put in, or the logical axioms. I don't remember what they all were now, the premises that we were using, of course, because this was decades ago. But was it a ton of extra work? Yes. But was it fun? Of course. That was why I did it, is I wanted to see how did these actually work out. And by that, it turned out I was actually doing the next chapter, which was going to describe how to do that, in advance. So, I got a leg up on learning why that was working. So ironically, it wasn't until after high school that I discovered number theory as a thing. And I know I've mentioned this before, but I'm just going to say it again. Number theory itself is why I love math, because it's like you're working with a puzzle and you're trying to figure out what's going on with this, right? You're trying to get you're trying to find the ends, you're trying to narrow down, and you're trying to experiment to break things again, right? I don't like the calculation of mathematics. That's boring and trivial. I like coming up with weird theories and then seeing if I can break math. That's where the fun is. It's in the visualization of something, and it's like you just poke it and see what kind of chaos you can cause. And it's safe to do this. That's the other key. Mathematics is a well-designed system. It's like when you have a well-designed computer program, you're not going to end up with doing something illogical with it if you're following, the actual steps. Even if it's counterintuitive, it's still logically sound. So you're safe playing with it. So I get, that was a bit of a bunny trail, but let me get back to the point. Part of the reason I bring up geometry right now is because the one thing about math that always bugged me in high school was how none of my teachers ever really explained how it was that a bunch of the Greeks back in the old days that was studying things on math before algebra was even a thing were able to form the basics of what would become algebra simply by drawing figures. That is to say, in my scholastic studies, I began with algebra 1 and 2, and then geometry. And from that, we then went to trigonometry and then, calculus. And that was just a continuous flow, except for the fact that the geometry was just kind of stuck in there. It felt like it was just thrust in there in an ad hoc manner because you needed to know this other thing. But when I was looking at the history of math, the Greeks only had geometry for their reasoning when they were doing what they did. And a lot of the stuff that we learned in trigonometry, they had solved without using algebra even. And we just kind of overlooked how they were able to do that because what we had learned from algebraic equations was simpler to use, right? And I'm not criticizing that. For most people, learning the simpler method is definitely ideal. I get that for a fact. But for me, I wanted to know how the Greeks did that. How can they just draw circles, triangles, squares, other shapes that they can get and end up proving these complex theories? Like just an example, how Euclid proved that there were an infinite number of prime numbers. He did that from geometry. His proof was built by looking at how lines intersect and what that meant from the remainders of lines in distances by units and things like that. That all came from geometry. We use mathematical formulas with numbers and things like that for it, and variables. But he did that with geometry, and no one ever explained how in any of my classes how they did that. And I realize now, of course, that it's because nearly all of my teachers were, and I don't mean this rude, but they were barely functional when it came to mathematics. In high school, teachers don't need to understand number theory or even really have the ability to do any math greater than the course that they're teaching. They don't have to follow a single mathematical proof. They just have to be able to explain what's in the book, right? That's, to me, not the best ideal, but that is the minimum that you need to have as a high school teacher. They just know the concepts of what they're supposed to teach. And again, I don't want to be overly critical, but I do believe this is the reason why in high school my best math teacher was my physics teacher, not any of my mathematics teachers. But again, not to be rude, but it is what it is. That is the reality. Also, the reality is, although I didn't know at the time that I already knew how this was connected, I actually knew intuitively what the Greeks did based on the underlying rhythm of mathematics. I didn't know that I knew that. So it's one of those ironies, because normally it's what Dunning-Kruger effect or whatever, where you think you know more than you actually do. And this is one of those cases where I actually knew more than I knew at this point. And it's a pleasant surprise to have it go that way. So what is it that I knew without knowing that I knew? It goes back to the original point. That stereo, those discs that were turning on the stereo. Numbers are nothing more than just ways to describe the behavior of loops. That's my simple observation. The numbers we use in mathematics, the digits themselves, are just arbitrary symbols assigned to certain patterns on loops. And because the fundamental pattern of the loop is objectively real, the symbolic representation of that pattern is also going to end up being objectively useful. Which is to say, we can substitute the label for the thing that it describes, and having successfully abstracted that concept, we can develop the abstracted version of it completely without needing to actually have that physical object anymore. That doesn't make the physical object not valid or necessary or the real fundamental thing of what's going on. Basically, whether you know it or not, you implement the nature of looping all the time in mathematics. For example, you don't need to spend any brain power to calculate what 5 times 10 is. I can just ask you, what is 5 times 10? And you immediately know. You just write the 5, put a 0 at the end. That's your result. You're not calculating when you do that. You just know the process is we have a 5 and we add a 0 at the end, because whatever you're multiplying by 10 just has the original thing with a 0 tacked on. And that's it. But what that is that literally is the looping mechanism that I was referring to, where when you multiply by 10, the middle wheel is the one that turns instead of the outer wheel. That's all it is. And once you realize that this is the pattern that's going on, you can spot some other loops that just come out of math. Consider this pattern right here. These are actually two patterns. So we start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let's turn around and go backwards, and we do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, back the other way. So what is this representing? It's just a loop of those digits. But it also happens to be the results of the 9's multiplication table. 1 times 9 equals 0, 9. 2 times 9 is 1, 8. 3 times 9 is 2, 7, and so on. The result of the multiplication that we see is 2 loops of digits going contrary to each other and put together. And this feature itself is not even just kept in base 10 mathematics. If we look at base 6, then we have the same result of the 0, 1, 2, 3, 4, 5. Remember, there's only 0 to 5 when it's in base 6. Reverse that, you get 0, 1, 2, 3, 4, 5 going the opposite way. This is the same thing as 1 times 5 is 0, 5. 2 times 5 is 1, 4. 3 times 5 is 2, 3, and so on. Now, what I love most about these results is that you have one sequence increasing while another sequence is decreasing. But the results, the mathematical equations, are foreordained by the very nature of what numbers are. I mean, look, you can arbitrarily begin a sequence with 0, 1, 2, 3, and so on, and you can go up to any arbitrary base you want, reverse it, go back down, and you've got the right sequence. Base 16, for example, you can go 0 to F, because we start using letters, reverse it, and it's going to be the same multiplication of the 1 times the 15 in that, or I guess 1 times f is going to get you that exact sequence there. Think about this. If we didn't already start with what the base was, it wouldn't know that when you're doing this, it needs to end with that other number. That just falls out by the fact that we're using a loop within a base structure. You could basically go to infinity with this, and the infinite backwards would be your result as it's coming back down. And of course, I know infinities are not actual numbers, but you get the point of what I'm referring to this. Whatever the end of our string is found in the beginning of these looped sequences. And again, that's the kind of thing that blows my mind. All of mathematics turns out to be these hidden loop manipulations disguised as symbol shuffling in the form of digits. And that's why I love the factor field that I created, because it contains a lot of these same loops going in both directions through an infinitely long sequence. We have these reflection points, such as here. I call this a 6 spike because it occurs every 6 rows. And it also functions as a reflection, where what is above the spike is identical to what is below the spike whenever there's this line. And that means that when you're looking at the initial starting point of the factor field itself, you're simultaneously seeing what the end is. It's some far distant point, infinite distance away. And we are seeing that aspect of infinity back here at the very beginning. In a way, it's kind of like, suggesting that there's some kind of relationship between 0 and infinity, as if it's some kind of reflection point. And again, I'm not trying to get too esoteric with this. This is all formed because we're looping every single value one after the other. Again, the factor field itself is created by using these simple looping patterns. It's all possible integer loops here. You start with one right after the other, then it's one every other sequence. It's every 2s, then it's one every 3, then it's one every 4, one every 5, every integer. And it's just looping down the list as far as you can go. This pattern falls out of it. And the pattern that falls out is showing the reflection point going back up the pattern in a way where you're seeing that taste of infinity right at the beginning. Again, this is just a thing of how the mathematics loops. By talking about it in this manner, it definitely makes me sound loopy. But in my view, mathematics should drive you loopy. And with that, I hope you all do have a wonderful day.